Good morning, everyone. We are so grateful that you were able to attend with us. My name is Lisa Block. I'm the Director of Global Sales and Marketing here at Hybrid Manufacturing, and we are so grateful that you were able to join us for our webinar today. Dr. Jason Jones today will be discussing how hybrid modernizes factories. He has a wonderful presentation prepared for you today. And so as a quick reminder, I would love it if you would do me the favor of adding any questions that you may have into the chat. We will be holding these webinars once a month, just kind of for continuing education and to continue building awareness. Now, without further ado, Dr. Jason Jones.
Good afternoon to those of you joining from Europe, and good morning those of you in the Americas. It's great to see several familiar faces joining as attendees, and welcome. Also, if you're new to us, we're really pleased to have you. As I start, I would like to make today's conversation a little bit of a continuation from last time. And so I'll give you a little bit of background and a recap. A little background is that I like to think of things within different scales and different domains. And on screen, I have 4 words, and probably the narrowest and the one we talk about the most with additive manufacturing is at the bottom. We talk about parts. We talk about part quality. We talk a lot about those parts. If we think about moving up a scale, then we go to collectively all of the parts. How do we manage parts? How do we manage work in process? What decisions do we make that impact all of the parts collectively and how we move them around and how they flow through our manufacturing environment? Next step up is the equipment that we use, right? A lot of it's capital equipment, some of it may be handheld, but how does that impact what we're doing? And lastly, and most importantly, are the people. And if we think of across all 4 of these domains, you'll see this come up a couple of times throughout today, because I want to highlight at those different scales. Ideally, changes in manufacturing would positively impact all of those areas, not just 1 or 2 of them. So with that as a framework, let's look briefly at what we saw last webinar. We looked at this great feedback loop of how to get quality or how to know if we're producing quality. Many people who use additive, they've got tools and they make things and they think, how do I know what I've made is good? Particularly inside and also out. And the origin of that question has a really strong basis, particularly if you come to additive from a CNC machining background. You're probably used to buying in a billet where somebody else has already produced that billet to spec and has taken responsibility for the internal microstructure and the chemistry. So they're responsible for the inside, and only then the CNC operator is responsible for the outside. As we move to additive, the responsibility for what's inside and outside shifts as you do the 3D printing, because you establish both of those as you print. Unfortunately, the same assessment tools that are available to a steel mill or a research lab have not all migrated into 3D printers. And as a result, operators have capability, but not all of the tools for assessment to know if things are good. And we looked at what a hybrid all-in-one machine brings in terms of architecture flexibility and additional tools to help increase people's confidence without having to go to the extent of destructive testing or even CT and other very expensive testing methods. And we looked at that at each stage throughout the product life cycle, if you will, from when it's first created to its finishing processes to the assessment and what can be done in situ all in a single setup. Key to that was these scales. So we actually looked part scale, and we started at looking at only at the surface and went all the way down to full volumetric scanning. So again, a look at how you can tighten that loop, what data you can get, what you can't get, what's practical, and that was the last webinar. In today's webinar, we're going to go to the other extreme of scale, and we're going to look at how hybrid manufacturing really impacts and modernizes factories and factory layout, and what options you now have. As we consider this, this is the image for today that was the theme of the talk. And if you're not familiar with the silhouette, maybe you've seen a factory icon before, and it looks something like this. You'll notice one of the characteristics of a lot of icons that represent factories is this sawtooth roof. The sawtooth roof, just as a little historical aside, was developed in the early 1800s really as part of, as factories started to come onto the scene and people were in this great industrial revolution, buildings were getting very large. And to accommodate lots of people, and especially at a time when electric lighting was not yet widespread, they would orient these buildings so that the roof would actually block the direct sunlight, and then they'd put windows in the vertical sections of the sawtooth roof, and that would allow natural lighting into the center of these buildings that ended up being very large. Probably at this point, the largest buildings had likely been religious buildings. And then as they scaled even larger with manufacturing, this was a technique to get light in. So that's the sawtooth roof, and a characteristic of why we see this symbol. It sort of died out in its popularity in probably the 60s, 70s, 80s as electrical lighting became obviously it became widespread earlier, but there's been a revival of this sawtooth approach as designers have now been wanting to incorporate more and more natural light. So a little fun tidbit about factories and factory buildings. Within this silhouette, you can see there are three technologies. I'll just pause for a second, look at those, and see if you can figure out which is which. In the center, you can see a laser-based directed energy deposition. On the right-hand side is material extrusion, that's carbon fiber ABS. And on the left is eddy current inspection. And this icon jointly helps indicate, okay, we're looking at factory design and we're looking what hybrid all-in-one architecture can do for it. So let's look a little bit at factory history. In terms of workflows, my first experience with a workflow was in a garage at a workbench, as illustrated here. Probably many of you the same. As we then move on to a wider awareness of manufacturing, the preeminent figure, I would argue, in most people's minds must be Henry Ford. And he went from essentially a workbench type approach or a project type workflow, and he transitioned car manufacture to the very famous assembly line. In his case, it was actually a moving assembly line. And he was not the first to use an assembly line, but he certainly optimized and perfected it on a product and brought a scale and magnitude of production the world had never seen, which is amazing. And I think it's important that we recognize that. One thing that we inherit from this amazing accomplishment, and just out of interest, he died with a net worth of somewhere around 130 billion, most people estimate, which is an immense amount of just evidence of how successful this was. But we then carry forward with this idea of an assembly line and how efficient it is. And in fact, still in manufacturing today, you look at lean techniques, a lot of people still look to this assembly line where your parts flow through the factory, whether it's in a straight line or a U shape or something else. And this is the gold standard for the least amount of waste, the highest productivity, the lowest costs, and there's a lot of truth to that. Yet, particularly as we look at digital manufacturing and its abilities and the market now, our ability to produce different products has skyrocketed. The demand for products, the volatility is unprecedented. And as a result, many manufacturers need a new level of flexibility. For as many things as assembly lines do well, flexibility is not one of them. We all remember the famous line that you can have a Model T any color as long as it's black. So that helps, or it kind of forces us to reassess, okay, let's look at the different types of workflow that you can plan out in a factory. What are those layouts? And in three general terms, we have a project-based workflow where the project stays in one place. We still see this heavily adopted, especially for large things. If you've got a ship that's in dry dock, you bring all the tools to it. It doesn't move, right? Large airplanes can be the same. If we skip over to the far right-hand side of the picture, the assembly line, again, very well documented in people's minds and ideas, this flow through that's very linear and very efficient. And in the middle, we have a job shop. And a job shop deals with variety well, not with the same efficiencies as an assembly line, but generally it's laid out by departments or skill expertise, and the parts have to move to wherever that equipment and that expertise is. And I've shown a picture here of Proto Labs because I think they're a great example of a modern job shop with tremendous flexibility. So I'm going to ask a poll question now. If we think about additive and its use in production, which of those workflows is most widely adopted? All right, hopefully you've had a chance to select that. And as we go forward, the results on that, Lisa can update us, but there were several options selected. In most cases, additive manufacturing is used in some variation of a job shop from the research I've done. Now, it's important to acknowledge we've talked about 3 types of workflows. In reality, very few companies operate purely one of those. And so often there's a little bit of a mix and blend and crossover of those principles. But one of the reasons I answer job shop is mostly because the architecture of 3D printers is usually a self-contained box. That automatically makes it some variation of a batch process. You don't normally have a fixed tack time where, products come out of a printer every 5 minutes, for example. And as a result, it's very difficult to implement a traditional assembly line type of approach. And so that second bullet point, where you have variable design, and from those variable designs, variable processing time, this flexibility that digital brings, it almost instantly disqualifies you from using a traditional assembly line. And so most people then end up with some variation of a job shop. And a job shop is really flexible, but it's also difficult to achieve really high efficiencies. It can be a scheduling nightmare, frankly. So, but are there some exceptions to these principles that we've seen recently? And what we're looking for, and today I want to highlight the opportunity where you've got a string of manufacturing processes, a process chain. Are there times where instead of doing all this, you can simply do this? And so that'll be our focus today as we look at how hybrid manufacturing gives opportunities to modernize factories. And I recognize that these principles will apply to certain types of parts, and I hope we can identify the applications that are relevant to this approach so that you can make an educated decision of, well, this could be useful or it doesn't work for us. As background for those of you who may be joining us the first time, as a company, we've seen this opportunity to change the architecture of things. Over several decades, maybe even 50 years now, we've seen machine tools transform from individual single setup machines that do just one thing and converge into multitasking machines. And now we're seeing the same opportunity mixing in additive manufacturing. Can we now take all of these principles, co-locate them into a single machine, and an all-in-one hybrid machine is the epitome of this convergence, not just of subtractive tools, not just inspection, but additive, subtractive, and inspection altogether. Who we are the pioneers in bringing directed energy deposition, which is one type of additive, into CNC machines. We also pioneered material extrusion into CNCs. Because of our open architecture approach, we are the most adopted on commercially available hybrid machines and have a strong foundation with our patents. I'd like to talk just another comment about an open architecture. For us, a hybrid machine should be flexible enough you can feed into it the different types of tools and heads that you need. And so as you look at how that works, we'll take a base machine, typically a milling machine or a robot or a gantry. We'll add to it a variety of ancillaries, which can be digitally controlled. For example, this is a head that deposits carbon fiber ABS. It can go either into a spindle of a milling machine, which you see on the left, or on a robot. Once that's implemented, it could look something like this. Literally in a milling machine, you can add this tool in the place of a cutting tool and control it using the existing machine. The data is prepared using a slicer, but it outputs machine tool, G-code. So then these tool paths are followed, and you can see here this deposition. The walls that are being deposited there are more than 6 millimeters or 1/4 of an inch. So it's a very highly productive system. It's anywhere between 200 and 2,000 times faster than a typical desktop machine. Likewise for metal, you can use metal deposition heads, bring those tools into either a machine tool or a cell for, robotic work cell, and then they also go forward. And here's an example on a partner's machine. Switching back and forth between different heads is a key ability. And in that way, then you can start to mix and match these different types of things. I had a question come through the other day, and one of those questions was, can you use metal and polymer deposition in the same machine? And the answer is yes, because as we look at all of these different applications, we really have this suite of modularized tools that says, hey, you can then down select from these as if it were a menu, what you need to be able to address them. And as we do for today, talking about factory design, I'd like to focus on coatings and repair. So the first example I'd like to show you is about repairing blades. And the second example I'll show you is about making new molds. So if we go to the blade repair scenario, this is with our customer GE. And some of what I will share with you today has been publicized through articles. And some of it's a little bit additional. I'm grateful to them for allowing us to discuss some of what happens internal to them. If you're not familiar with repairing blades, it is a very intensive process. It requires a significant amount of capital and expertise, skilled labor to be able to do it. And pictographically along the bottom of this image, we've tried to show some of the general steps. Typically, the first step is a grinding step. It can happen in a milling machine or, well, a tip crop often is what it's called, but it's a removal step. It can be with a manual grinder or with a machine tool. You remove the worn or decayed material. The next step is that you add metal back. And it can be a robotic setup and fully automated. It may also be a TIG welder in someone's very skilled hands. And then once you've gone through that, you have to then clean up that surface, right? Welded material, and this also goes for 3D printed metal material, is not perfectly smooth and polished. You have to come back and finish it in some way. And that's what these latter steps are. To add to the complication, when we talk about repairing parts that have already been in service, they do not match one another, right? There's an original CAD drawing for sure. Often these parts are cast. Once they're cast, they don't match each other perfectly, but certainly after they've been in the field for thousands of hours in use, they're different. And as a result, this ends up becoming a customized process. Every single blade that comes in needs individualized attention. And for the longest time, operators, very skilled people, were the most practical way to do that. However, as CAD/CAM gets better and our ability to inspect and create a digital twin improves, now we're seeing CAD/CAM solutions that can adapt to each new blade presented to it and be scanned on the fly and then move forward. So it's a really exciting time. And GE got this hybrid all-in-one machine and they said, okay, how are we going to assess it? We're going to do it stepwise. So they put it in a production development area just alongside their main workflow for repair. And then they take each step one at a time. They would siphon parts off. So instead of flowing through their normal, path, they would come over to this hybrid all-in-one machine and they would do one of the steps and remerge it back in with the flow. Here's an example of a couple of steps that were done. So again, these images are courtesy of GE, but on the left, you see a squealer tip repair. This kind of top thing that looks like a Nike swoosh is one of the features on blades that some manufacturers use. And so on the left, it's as deposited. You can see it's gray and a little bit rough. On the right is after milling. And so this was proved out in a sequential sequence and then followed on by other types of repairs as well. And I'll zoom in here. This is another blade, an aerospace blade. And this really highlights that blend machining, which is at the end when you're going to try and get the mismatch between the original and what you've added to be as small as possible. And the tolerance for that is very tight, typically less than 20 microns. And with a well-calibrated machine, we've found that that can be hit within plus or minus 10 microns, sometimes better. So very exciting. So once these had been all proved out in a piecemeal fashion, then they were able to be brought all together. So then parts could completely be diverted. Once they'd been, arrived and been unpacked and uncrated, there was a large proportion of steps that could be completely skipped if they put them into the hybrid all-in-one machine. And as I visited and various conversations, one time one of them said to me, "Do you know what you do for us?" And I said, "What's that?" And they said, "You simplify our lives." And I love that as a brief summary. How do you know when it's time to adopt a hybrid process? If it will simplify some of your life. And much of the demand and driver for adoption, it was not new technical capability. They already had all of these individual steps in-house. It was the ability to smooth out their workflow, to make it more efficient, and to get a much higher yield in terms of quality without the variations that came. So I'm coming back to this multi-scale, multi-domain sort of framework. And I'd like to talk about each of these. And we'll start small with the part. By moving from a traditional welding process, whether it's automated or by hand, it's typically a TIG or sometimes a microplasma type approach. Often the microstructure of what can be done in a laser-based approach will give you a much finer microstructure. That's highly desirable for many material properties. Another thing is that the heat affected zone, the amount of heat that you put into that part is far more localized and much smaller. And so the heat affected zone is much smaller as well, which is typically a weakness of welding. Because you don't have to move this part around, it's much easier to maintain accuracy. Even if you're accustomed to using fixtures and moving in between different setups, the time and energy and cost of doing that is reduced. And because you have a high accuracy process and your deposition is very near to net, you end up depositing a much smaller proportion of metal. And therefore you have to remove lots less metal. And so that cycle time can be sped up. If we think about managing parts collectively, right? We already mentioned the need not to move them around. What also happens is when you have lots of capital equipment that's high value, because it's such high value, management philosophy says we need to fully utilize these things. And as a result, what you end up with is piles of work in process in front of each piece of capital equipment to ensure its utility is high, right? Your utilization of it is very, very high. And that work in process has a cost, it has a value, just the individual pieces, but the cost of moving it and storing it and managing it is often overlooked. And if you pause to then really try and look at what that cost is, it can be very substantial. And so as we move toward fewer fixtures, less setups, and probably less pieces of capital equipment, we start to look at, okay, the value of the work in process. And if you just are able to look around your facility, calculate the value. It's not uncommon to have hundreds of thousands and sometimes millions of dollars worth of work in process sat in piles in front of a machine. And the mentality is, I'm getting great utilization of that machine. And yet, in many cases, the unearned revenue from that work in process would justify significant investments into the manufacturing facility if it could be put to work. And so you can look at that return scale, and often it can be as short as even 3 to 4 months, often longer. But look at what you could do with a 70 or 80% of that work in process out in the field making money, rather than sat waiting to be used on a large piece of equipment. So this is a different way to think about it, and an invitation to you all to just look at, if I reduce my work in process, what would that do for me? If we look at capital expenditure and the capital equipment itself, line balancing is one of the biggest headaches of all types of manufacturing workflow. Getting all of the parts to have a similar amount of time that it takes to do the removal, to then move on to a separate station for adding, to a separate station to finishing. You don't have to do that if you do everything in a single setup. If it takes a little bit longer, it takes a little bit longer, but it doesn't displace and make all of your other system not operate efficiently. So that is a really powerful motivation for moving toward a hybrid all-in-one setup. You can also achieve, so we call this parallel processing. Historically, what GE had been doing was sequential processing in a serial process. If we borrow from the computing world, then we say this is parallel processing. You can actually achieve the same output of a serial setup, often with two hybrid all-in-one machines. And if we think about it from a cost perspective, what do these things cost? If you want to get into a repair cell, the cost of a serial setup where you have 3 different dedicated pieces of equipment, or often 4 or 5, this is just a simplified slide, is often far greater cost than a single hybrid all-in-one machine. So it's a lower cost to enter if you want to get into it. It also is more self-contained. So if you want to distribute that more around the globe, you certainly can. So all in all, when we start to look at the reduction of capital equipment, we've seen as much as 50 to 70% reduction in capital equipment requirements, along with the floor space requirements. And that suddenly becomes a very powerful thing, especially if you greenfield a new manufacturing facility. These are opportunities that are ripe now for you to benefit from. And lastly, if we look at the human aspects of this, you go from what largely involves manual moving of lots of parts all around. These jobs are high pressure jobs, and the consequences of making a mistake are very, very high. To systematize it in a digital environment allows systematic correction to be much easier. We actually did a different study with Cummins, and we looked at where many of the mistakes happen and where the rework is caused from. And we found that by automating, up to 95% of the mistakes could be omitted or at least systematically taken care of, which was really a revealing number. For the humans as well, as you move to an all-in-one setup, you reduce the number of machines, machine controllers, software packages, post-processors that you have to know. And so you're able to unify that workforce, those operators, and make them more cross-functional, so that if somebody is not well or out or needs to do something else, you can mix and match your operators far more easily. They also tend to be working on a smaller area in terms of shop floor, so they're not walking around as far or as often. There's another piece of the puzzle that came to bear specifically when GE had an accident. They crashed one of these all-in-one hybrid machines and found that if you have multiple hybrid machines, you have full redundancy. And so you're able to still get throughput through those other lines because they're not dependent on one another. So whereas with a serial setup, their interdependence means everything stops. And the ability to continue at 2/3 production is really a powerful thing. And in fact, in the case of GE, what they did is the machine that went down so they were doing additive, subtractive, and inspection. They crashed the additive head. So they were still able to do subtraction and inspection. So what they ended up doing is repurposing this machine that was down for about a week and a half, only to do subtractive and inspection. So in that way, they actually got more than 2/3 throughput, or were potentially more than 2/3 of their throughput through. So this resiliency, the independence or interdependence, avoiding the interdependence of serial, is another powerful thing for consideration. So let's shift to another customer of ours and a different field entirely. This is making molds, and these are new molds. So I call this mold enhancement. And you can see this glass bottle up front out of focus. These are molds for making glass bottles. and it's with a customer of ours, Moldies Medellin, which is part of the Ross International Group. And again, we thank them for being willing to share some of what they're working on. As we zoom in and look at this mold, hopefully you can see my cursor. This edge right here, it's just the edges of this mold that are receiving metal. The rest of it is cast and then milled like normal. But the additive step is right here on these edges, and it brings tremendous value. And let's explain why. If we look at the glass bottle mold manufacturing process, the glass bottle manufacturing process generally, typically you use two molds. On the left, you see a pre-mold and then a final mold. Okay, the glass, which is orange, comes in, air blows its initial shape, which ends up being the top of the bottle. It gets flipped over, and then air is blown in a second time, which forms the rest of the bottle. And in practice, it looks something like this. So here you see glass gobs coming down through the ceiling. They're getting farmed out to an array of different molds. It feels a little bit like shooting stars when you're inside an environment like this. It's really neat. It's also very hot and very loud. Here you can see a bottle just coming out of that mold. That mold will close. This is actually the pre-mold side. Here comes the glass. It'll get capped and air will get blown into it, and then it gets moved over to the final mold. Here's the final mold. Once again, it's going to close. They'll cap it, they'll blow air into it, and that'll be the final form. One of the big drivers for the cost of these bottles is how fast they can get these glass bottles to cool down enough so that they can be self-supporting and go get annealed. And you can see these molds are gray. They're gray cast iron, and they're gray cast iron because it handles the abrasive molten glass very, very well. The problem is it doesn't get rid of heat super easily. So the desire is to switch this material from cast iron to bronze, since bronze will get the heat out far quicker and allow you to run that line faster and bring down the cost of each bottle. And so the transition to bronze is highly desirable, but there's a little issue. The bronze is softer, and so the edges don't survive as well. And if they do get damaged, they can't be repaired very easily. And so what has been happening is conventional welding has been used to add nickel-based superalloy along these edges. And the process ends up being really quite extended. This is a summary slide, but if we look at it in more detail, this is actually what happens. You start off on the left by milling, rough milling. That rough milled casting then goes to be preheated. It has to be preheated until it's glowing red for conventional welding not to crack it. That's about 20 minutes. Then it goes into a welding setup, which is minutes. Once it's welded, it has to go, it's supposed to cool for 8 hours so that it gets to a dimensionally stable place before it can go on for a milling step. Now, if it were only this complicated, it would certainly justify trying to hybridize and co-locate some steps. But what actually happens is the very characteristic that they're after in performance of the mold, which is the ability to draw heat out, also causes them to have to repeat this cycle of preheat and deposition because the mold won't stay hot enough for long enough to do all the welding that's needed. So a portion of the welding happens, a portion of that weld gets milled away, and then they reheat it, do the whole thing all over again. And so you can see these 8 or 9 or 10 steps are a lot of steps. And so as we look at it with new eyes and say, okay, we can now do additive, we can do it within an architecture that's flexible. Let's see what makes the most sense. First off, let's replace the conventional welding with a laser-based weld. What that will allow us to do is skip the preheat and cool down cycles. By skipping those, then we say, okay, where are the other processes? Well, you got multiple processes in a milling machine. Well, let's take that laser-based deposition, let's put it in the milling machine itself, so that then your common denominator is milling machines. You no longer need the robotic line. And because now we're all common in a milling machine, and we can bring multiple processes to these parts, we can actually eliminate every one of these transfer steps until the part comes out of the machine to go downstream for final inspection. So in that way, we really bring a before and after that's a tremendous boon and boost to efficiency by consolidating those things into a couple of hybrid all-in-one machines. And so this is another process simplified by hybrid all-in-one. And if we look once again at this set of scales and domains and go to part level, you'll look here on the left. We've got a before and an after shot. If you look at the weld here in the before, you'll notice that it's somewhat ragged. This is an indicator of how much heat input and how much that metal mixes in that dilution area, and consequently it has quite a large heat affected zone. Over here on the right with ambit, it's a laser-based process. You can see it's a very nice straight line by comparison, and it's a much, much smaller dilution zone and heat affected zone. And that then bodes well for its future life, where not having that zone, which is susceptible to other things, can dramatically increase its lifetime. If we look at parts and managing parts, again, we get a tremendous drop in work in process. Looking at CapEx, they have decided to unify on a 5-axis machine, and you can see there, this is in their facility, this is multiple 5-axis machines, which are now hybrid all-in-one machines, and enables this simplified workflow where line balancing largely goes away and they're able to simply produce. And lastly, for the humans, again, we've got a single set of CAD CAM with largely a single person that's able then to prepare all of these things for these machines. Single post processor. It just gets much, much simpler when it comes to the additive, subtractive, finishing steps. So that before and after works really well. And I'll just highlight in this particular part, part of the reason it works so well is by transitioning to a laser-based additive process, preheat and post-heat, cool down, were able to be eliminated. So that's a nice characteristic to watch for. So just as a bit of a recap, when we have open architecture hybrid machines or open architecture machines in general, we can cope with variability and do so with far higher efficiencies than a traditional job shop because we don't have to be moving all of this stuff around. We can eliminate line balancing and reduce work in process and therefore reduce the capital equipment requirements, the space that it takes up, and make things simpler and less stressful for operators. So revisiting these different types of workflows, really we've hybridized between them and achieved flexibility with larger efficiencies. And I should emphasize, these can be intermingled and mixed and matched. We've worked on a variety of machines that also move parts as well. So if we consider a hybrid all-in-one being able to have tools flow through it, it can also have parts flow through it. So you can think through that so that hopefully you can end up doing something that's very far simpler instead of a much longer process. We talk about long supply chains and how shorter supply chains are more secure. And I would argue the same is true for production parts. If we look at process chains, shorter process chains are more reliable. They're easier to maintain and more predictable. So in this sense, we're really enabling greater flexibility with efficiencies and redefining what the conventional knowledge has been, obviously with a nod to Ford and the assembly line and the heritage that we build upon. And we're really grateful to have had this chance to talk with you today. Thank you very much. Lisa, I am now ready for questions.
Awesome. So what type of parts fit this approach best?
So the automating of lots and lots of processes in a single setup, it works in a couple contexts. One is if you're adding a small amount of metal, a relatively small amount of metal to an existing part. You'll see that both examples I chose today, it's kind of a small amount, maybe 5 to 10% of the total part that we're adding. And often we add to a casting, a forging, even 3D printed parts as well, something from a powder bed fusion machine you can add on to.
And so is preheating necessary?
When you transition from often an arc-based or plasma-based process to a laser, photons from the laser behave differently than the electrons in an arc. And so your heating effect is far more localized. So it opens up that window. There are still materials that need preheat with a laser, but I would say you could maybe get a third to half of the materials that would normally require preheat that don't with a laser. And where they do require a preheat, often it's a lower preheat requirement.
Thank you. And so what is the contribution that this technology makes to consumable wear parts?
When you say consumable wear parts, whoever asked that, I'm thinking of things that get used in the field, whether it's cutting tools or downhole where you really got things that are going to get worn away, whether it's in a pump or a drill or something like that. We see this workflow as a new workflow. We've seen it firsthand at customers where, and I have to credit Modernizes as being one of the first companies that saw this and said, we're going to try and optimize the 90% of our production in this approach. And it's been an amazing transition to watch them as an organization look at it and say, this is the way, and to garner the efficiencies from that. So you've seen two patterns today where that works really well. And I think the wear parts are great because usually it's just a layer, right? It's a relatively small amount of what's being added. And if we look at from an application standpoint, this top little section, which talks about coatings and repair, both of these tend to be really good candidates. As you move into adding features and growing parts, this workflow can be efficient, but you have to look at it in more detail where it's more cut and dried over here on the left where you're adding 1 or 2 or 5% of the volume of a part.
And then how do I look at a business case to decide if it would be beneficial to adopt a hybrid process?
At a really general level, you have to ask yourself, is this going to simplify things? And you really need 2 or 3 pieces of data. You need to know your process cycle times for each individual process. So how much adding time do I need? How much subtractive time do I need? If you're already doing remanufacturing or repair or even hard facing, you probably have a baseline for that from manual processes. If it's new, then you need to get an estimate. And so you could get a quote to say, how long will this take? And based on those numbers, then you can say, does this add up? Does it actually drive value back? And often we're seeing savings of 50% or more in the end, right? On individual processes, you might be over or under, but if collectively you can then drive and drop 40 and 50% out of the cost of something, that's savings worth moving for. It's worth changing for.
And is this an assessment that hybrid manufacturing technologies would be willing to assist with?
We're happy to. Yeah, we're not experts at every process, but certainly the different tool heads that we have perfected, we're very versant with and happy to consider it. And if it doesn't fit what we do, we're happy to tell you that, look, this is better as separate standalone machines or different additive processes.
Thank you. And so then how do we start adopting a hybrid process?
The first thing I would say is to, obviously you need to discuss it internally, but as you look at what your time and your cost inputs are, you can then have a dialogue that says, could this be useful? I've watched in every organization that's done it. It's a management change, right? It has to be a management approved change. It can't just be somebody technical. It's too large of a change when you're going to really revamp the flow of parts on a regular basis through your facility. And so it starts with the technical case. You then have to build that business case and make sure it's strong and robust. A lot of those savings values that we showed both in blade repair and also on the mold, those are what you have to add up so that it justifies it. In general, I would argue that most, particularly job shops, don't account very well for time and motion. They account for the capital equipment, they account for the active processing time, but they don't account for everything else. So I would say, hey, what about this cool down time? Oh, we don't count that. Well, if you're in a remanufacturing environment and turnaround time is your distinguishing factor, all of a sudden, and particularly at mold days where, our glass bottle mold manufacturer, you take a process that requires a minimum of 4 to 7 days and you shrink it down to a minimum of a day and a half, or the actual steps for adding and you go from 4 days to 40 minutes, something like that. That's a huge savings, and it allows you to capture those urgent jobs and urgent customers and treat your best customers with that amazing turnaround time. That's a competitive advantage. And I think it's one that needs to be considered and vocalized in the process.
And then, as you know, there are lots of machines on the market, lots of different brands, so many decisions to make. Can I add this technology to any machine?
I would say most machines, this can be added to. There are some exceptions where it doesn't make as much sense. Vertical machines are easier, but in general, there is no machine style that it can't be done. We've done, all different types of milling machines, gantry machines, robot, parallel kinematic machines. Literally, I can't really think of a digitally driven platform that we have not been able to add this equipment to.
Thank you. I'm going to take a couple of seconds and ask if there are any further Q&A questions. We can take those questions. If you need a few moments to enter them, we're happy to answer those questions for you. I'm going to make sure we give you some time because I know that there is a slight delay. So I wanted to make sure that we... Okay, Jason, in considering this for my production, what would be your best recommendation as to the process of implementation? What does that process flow look like?
Typically, it's choosing one part or one family of parts that you think is the best candidate and running a little pilot trial and saying, okay, does this work? Can it work? And then assessing the quality of it. If the quality is good, then you go forward with far more confidence. But generally, if somebody comes to us with a specific part, it's very easy to establish quickly, does this work or doesn't it? When people come with kind of a more general idea, then often we have to pick something specific to actually get down to the nuts and bolts of how profitable it will be.
I've seen your heads on multiple brands in the market. Which is better?
Which brand is better? That's a very difficult question. We see different manufacturers take different approaches with their machine tools, and it really comes back to we have to identify an individual case. If you look at a part that's long and round, and obviously you're going to need some variation of a mill turn, and then you're able then to go through the various individual ones. And we've seen a wide variety. People who already use a specific brand of controller in-house want to match that controller. Part of the reason, and we had this dilemma as a company 7 or 8 years ago, we said, are we going to build lots of machine tools? And the answer was, there's so many great machine tool builders. We'd rather partner with them and be able to provide this on most any platform. And so we're happy to give you some direction when it comes to here's the type of machine you want, but often you'll have a choice of 1 or 2 or 3 different brands. And a lot of it comes down to personal preference. Again, machine tool, the whole machine tool world, from my perspective, it's kind of amazing the amount of technology you get for the money. And I hope that helps. But if we go to specific applications, if you say, here's a part or 3 or 4 parts, what machine, that discussion becomes really, we can just get to the point very quickly.
Okay, thank you. And then I have another question. It says, can you provide subcontract services so that I can be happy with the technology before I make this investment?
The answer is yes. Yeah, and we have significant demand for that. And we're happy to work with you and make sure that it's a real thing and that it actually functions and you can test it in the field and make sure that it's all great. And then we can all go forward with confidence.
And for our last question, I just want to redirect back to the differences between the machine tool builders. Do all of the hybrid products that are available in previously existing machine tools ready to ship, is that something that hybrid can facilitate for the client, or does the client always have to go to the individual builder themselves?
Sure, we're very happy to do turnkey solutions and do it regularly. There are a couple of types of machines where we would point you to the machine tool builders for sure. But in general, you can certainly do a turnkey with us, and we're happy to deliver that as turnkey.
Awesome. Thank you so much, Jason, for taking the time to do this presentation today. Thank you all for attending. As always, if you think of some questions that were not answered for you today, feel free to email us at marketing@hybridmanutech.com. We want to make sure that we get all of those answered for you. If you have any inquiries about machine recommendations or anything like that, we are here to assist you through this process. We truly hope that you enjoyed today's session. Our next session is going to be called just What is Hybrid Manufacturing? And it is Thursday next month, August 27th. The times are listed accordingly. If you have had the fortune of attending this webinar, you do have the option of just being automatically invited to the next one. We hope that you will come back. We look forward to seeing you. And we hope that this conversation was profitable for you and that you leave armed with some great information. As always, we truly appreciate you. And thank you so much for sharing your time and for attending today. Have a wonderful day.